63 light-years from Earth, in a star system that astronomers have been staring at for decades, something was hiding in plain sight. Beta Pictoris is not some overlooked corner of the sky. It is one of the most scrutinized star systems in modern astronomy. Researchers have aimed major telescopes at it for 40 years. It hosted the first exoplanet ever directly photographed. It has a debris disk so large and so bright that it transformed how planetary scientists thought about young solar systems. If any system in the galaxy should have given up all its secrets by now, it is this one. It had not. Hidden inside the data, tucked behind the glare of its own debris disk, was a third giant planet. A world at least twice the mass of Jupiter, orbiting at a distance comparable to Neptune in our own solar system, sitting undiscovered for over 11 years while some of the most powerful telescopes humanity had ever built looked directly at it. The planet wasn't on the edge of the system or buried in some inaccessible corner of the sky. It was right there, in the data, in archived observations, in a system that scientists considered one of the most thoroughly understood in the neighborhood of our sun. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Nobody found it until they weren't looking for it. That is the part that should make you stop. The team that discovered Beta Pictoris was not running a planet search. They were studying the atmosphere of a planet they already knew about, using an instrument in a mode that had never successfully detected an exoplanet before. The discovery was an accident. A signal appeared in the data where no signal was supposed to be. Not a faint whisper that required months of follow-up to take seriously. A clear, unmistakable chemical fingerprint. A pattern of peaks and troughs in the spectrum that matched the atmosphere of a giant planet, sitting in a part of the frame nobody had been watching. Here is what makes that matter beyond Beta Pictoris. If this system, the one with the famous disk, the landmark direct image, the decades of continuous observation, was hiding a planet this large for this long, then the question is not whether other systems are doing the same thing. The question is, how many? Astronomers have studied dozens of young stars with debris disks. They have collected archives of data going back years. They have looked with coronagraphs, with infrared cameras, with every standard tool available. And they may have been asking the wrong question the entire time, looking for brightness when they should have been reading chemistry. The discovery of Beta Pictoris doesn't just add a planet to a list. It changes the method. It opens every complex, dusty, previously stubborn system to a new kind of scrutiny. It suggests that the next generation of planet discoveries may not require a bigger mirror or a better orbit. They may be sitting in data that has already been collected, waiting for someone to know what to look for. To understand why that matters, you have to understand what kind of place Beta Pictoris actually is. Beta Pictoris is hotter and brighter than our Sun, the kind of star that burns through its fuel faster and lives a shorter, more violent life. It sits in the constellation Pictor, the painter, a faint southern constellation that most people in the northern hemisphere have never heard of and will never see. From the right latitudes on a clear night, you can spot it without a telescope. It glows at roughly magnitude 3.9, not the brightest star in the sky, but steady, blue-white, unmistakable once you know where to look. Its surface temperature runs somewhere around 8,000 Kelvin, compared to our Sun's 5,778. It puts out roughly 8.7 times more energy. By almost any measure you care to apply, Beta Pictoris is a more powerful object than the star our entire civilization depends on. But here is the thing that matters most about Beta Pictoris. It is young, almost absurdly young by stellar standards. Current estimates put its age somewhere between 20 and 23 million years. That number might sound enormous. It is not. Our Sun has been burning for approximately 4.6 billion years and has another 5 billion or so left ahead of it. If you compress the Sun's total lifespan into a single calendar year, Beta Pictoris formed sometime around the middle of December. It has barely started. If our Sun is a person in their mid-40s, mortgage paid down, career established, fully aware of what the next few decades will probably look like, then Beta Pictoris is a teenager who just got their driver's license and still hasn't decided on a college major. The system has not finished becoming what it will eventually be. The implications of this youth extend far beyond simple age. A 20-million-year-old star system exists at a pivotal moment in planetary development. The initial collisions and mergers that assembled planets from planetesimals are mostly complete, but the dynamical rearrangement and fine-tuning of orbits continues. Planets are still being scattered by gravitational encounters. Moons are still being captured or ejected. The system retains far more debris and dust than our own solar system does today, creating an environment of ongoing construction and reconstruction that makes the fundamental processes of planetary system assembly visible and measurable. What does that actually mean in physical terms? It means chaos, not the metaphorical kind. Real, ongoing gravitational chaos that our own solar system passed through more than 4 billion years ago and has long since settled out of. Around Beta Pictoris, planets that formed out of the original disk of gas and dust are still migrating, drifting inward and outward under the gravitational pull of everything around them, jostling for stable positions they haven't quite reached yet. Smaller bodies, the rocky fragments and icy leftovers from planet formation are still colliding constantly, grinding down, producing fresh dust that replenishes the disk. The system looks the way ours once did, back when the inner planets were still being hammered into shape, and Jupiter was carving its way through the solar nebula like something that didn't care what was in its path. For astronomers, this is almost unfairly useful. We cannot go back and observe our own solar system in its youth. Those processes are finished. All we can do is study the evidence they left behind, the craters, the orbital resonances, the compositions of asteroids and comets that carry chemical memories from the early system. But with Beta Pictoris we get something different. We get to watch it happen. The processes that shaped our solar system are still running in Beta Pictoris, still visible, still measurable. It is not a perfect analogue. The star is more massive than our Sun, which changes the timescales and the dynamics, but as a window into the physics of young planetary systems, it is one of the best we have found. Proximity helps. 63 light-years is close. In astronomical terms, many of the most interesting young star systems are hundreds or thousands of light-years away, which means even our most powerful telescopes see them as faint smudges with little resolvable detail. At 63 light-years, Beta Pictoris is close enough that telescopes can actually distinguish individual structures in the system. Features that would be hopelessly blurred at greater distances become resolvable. Planets that would be lost in the noise at 1,000 light-years might, with the right instrument, be detectable. This proximity has made Beta Pictoris one of the most intensely studied individual star systems in planetary science, not because it is the only interesting young system, but because it is close enough to the details are actually accessible. This resolving power matters enormously in practice. Early observations of Beta Pictoris, made decades before modern adaptive optics and space telescopes, could barely make out the disk structure. Today's instruments can identify specific features, asymmetries, gaps, warps, plumps, that reveal the presence and position of unseen planets. Spectroscopy can reveal the composition of the dust. Infrared measurements can map temperature variations across the disk, indicating where material is being stirred up by planetary perturbations. Each of these capabilities exists because the star is simply close enough to warrant the investment in observation. The result is that Beta Pictoris has spent the last several decades accumulating scientific attention at a rate most stars can't match. observing campaigns, dedicated telescope time, papers analyzing its disk, its planets, its stellar wind. What that sustained attention has built up is something valuable. A detailed record of a young system evolving in real time, with enough baseline that changes can actually be tracked across years and decades. When something new is found in the Beta Pictoris data, and something new keeps being found, it can be set against decades of prior observation. The context is already there. The star itself has a mass about 1.75 times that of our Sun. It is classified as an A-type main sequence star, meaning it falls into the category of hot, luminous, relatively massive stars that tend to burn bright and end early. A-type stars don't live as long as our Sun will. They don't need to. They have more fuel, but they burn it at a rate that makes the whole enterprise shorter and louder. Beta Pictoris will not be a middle-aged star in another 4.6 billion years. It will be long gone. But right now, at 20 million years old, it is in its prime. Stable enough to host a developing planetary system, active enough that the system around it is still visibly in flux. That combination, young enough to be chaotic, close enough to resolve, bright enough to study, is what turned Beta Pictoris into a reference point. When planetary scientists want to discuss what the early solar system might have looked like, Beta Pictoris is often where the conversation starts. It is the closest thing we have found to a snapshot of our own beginnings, still running, still evolving, close enough to read, and wrapping around the entire system, visible even in early telescope observations, was a feature that made Beta Pictoris unlike almost anything else astronomers had studied. A vast disk of debris that told a story nobody had fully cracked. When a planetary system is 20 million years old, the chaos that created it has not finished settling. 20 million years sounds like an enormous stretch of time. It isn't. Not for a solar system. Our own system passed through this exact phase more than 4 billion years ago, before complex life existed on Earth. Before Earth's crust had even fully hardened into something solid. The geological record we use to understand early Earth doesn't reach back that far clearly. We have almost no direct window into what our solar system looked like when it was this young. Beta Pictoris gives us one. That is the thing that makes astronomers genuinely excited when they talk about this system. Not just that it's nearby, not just that it has a famous disk, but that it is catching a process in mid-motion that ended in our neighbourhood before we had any way to watch it. Here is what mid-motion actually looks like. The planets in a young system are not sitting quietly in fixed, clean orbits. They're drifting. Gravitational pressure from the disk itself pushes planets inward. Interactions between planets push them outward, or inward, or into resonances that lock their orbital periods into mathematical ratios. The whole architecture is negotiating with itself. Jupiter and Saturn in the early history of our solar system are believed to have migrated dramatically. Jupiter swinging inward first, then reversing outward as Saturn caught up and their gravitational relationship changed. That migration reshuffled everything. It likely scattered icy bodies inward toward Earth, possibly delivering water. It cleared the asteroid belt. It pushed smaller, rocky planets into tighter orbits closer to the Sun. The solar system we live in was shaped by events that happened when it was roughly this age. We don't have a recording of that. What we have is Beta Pictoris. At 20 million years old, the Beta Pictoris system still has planets doing the thing our planets finished doing 4 billion years ago. The disk is still full of material, not gas mostly, because the gas clears faster, but rocky fragments and icy leftovers grinding against each other in slow collisions that produce fresh dust continuously. This is not a peaceful place. Kilometre-wide chunks of rock and ice are running into each other all the time, breaking apart, grinding down, generating clouds of fine particles that scatter starlight and make the disk visible from 63 light-years away. The disk is as bright as it is precisely because this grinding process is still active. In an older system, most of that material has been swept up, collided into larger bodies, or ejected into rely. The disk fades. Beta Pictoris hasn't reached that point yet. What this produces for astronomers is something almost impossible to replicate any other way. You can build computer models of what a young solar system should look like, you can run simulations, but simulations require assumptions, and the early solar system left us almost no direct measurements to check those assumptions against. Beta Pictoris is a check. Every observation of the disk's structure, its thickness, its brightness at different distances, the rate at which it's losing material, can be compared against the models. Every place the models are wrong tells you something about what the models are missing. The disk's structure is the really interesting part. It isn't uniform. It isn't a smooth, flat sheet of material spreading evenly outward from the star. It has gaps. It has edges that are too sharp to have formed randomly. It has a warp in its inner region, a tilt that bends the disk slightly out of its own plane. One side extends slightly further than the other. These features are not accidents. Each one is a gravitational fingerprint, the trace of something massive nearby, pulling material into patterns that reflect its presence. A planet carving through a disk leaves these kinds of marks the way a boat leaves a wake. The wake tells you a boat passed, even if you missed the boat itself. Astronomers have been reading Beta Pictoris's wake for 30 years, trying to figure out exactly what left it. Some features had explanations by the time Webb launched. The disk's warp, for instance, matched fairly well with the gravitational influence of the largest known planet in the system, which sits at an angle slightly off the disk's main plane and tugs the inner material into that tilt. But not all the features matched up. The sharp inner edge was one, that kind of abrupt boundary, where material stops as if hitting an invisible wall, is exactly what a planet produces when it clears a zone around its orbit. The two confirmed planets didn't put anything in the right location to explain it. Either the models were wrong, or something was out there that hadn't been found. This is the slow pressure that builds behind a discovery like Beta Pictoris d. Most single observation screams that a planet is missing. Instead, you accumulate 30 years of disk measurements that don't quite add up, 30 years of models that need one more piece to close cleanly, 30 years of a system that keeps offering hints it hasn't finished telling you everything. The researchers who study Beta Pictoris are not careless people. They are some of the most detail-oriented observers in planetary science. And for 3 decades, the disk's inner edge sat in their data like a question without an answer. The planet that would eventually answer it was already there. It had always been there. But finding it required something the field didn't yet have, a way to see past the glare of the disk and the star and the other planets, a way to read a signal that no instrument had yet been built to pull out cleanly. For all those years, the system's most famous feature was the debris disk, and its most famous scientific contribution was still coming. All of that changed in 2003, when a team pointed a telescope at Beta Pictoris and did something that had never been done before. Before Beta Pictoris b, nobody had ever taken a photograph of a planet around another star. That sentence sounds simple. It isn't. For most of the history of exoplanet research, actually seeing a planet orbiting another star was considered effectively impossible. Not difficult, not waiting on better equipment. Impossible in a practical sense, because of a number that breaks your brain problem. A star like our Sun outshines any planet orbiting it by roughly 1 billion to 1. 1 billion. Trying to photograph a planet in the glare of its host star is like trying to photograph a firefly sitting next to a lighthouse from 50 miles away. The firefly is there, you just cannot see it, and so for decades nobody tried to photograph exoplanets directly. Instead, they watched for shadows, or listened for wobbles. The indirect methods worked. Radial velocity picked up the gravitational tug of massive planets pulling their stars slightly back and forth. Transit photometry caught planets drifting across the face of their stars, dimming the light by a fraction of a percent. By the early 2000s, astronomers had found dozens of worlds this way, but every single one of them was inferred. A ghost planet, detectable only through the effect it left on something brighter. What nobody had was a picture, and without a picture, certain kinds of science were simply unavailable. You could infer a planet's mass and orbital period from indirect data. You could not study its atmosphere directly. You could not watch it move. You could not see where it sat in relation to the disk or the other planets. The image mattered, and getting one seemed almost too hard to attempt seriously. The coronagraph changed the math. A coronagraph is a device that physically blocks the light from a star inside the telescope itself. You mask the star out, and anything close to it that would otherwise be drowned in the glare becomes visible. The first coronagraph was built in the 1930s to observe the Sun's outer atmosphere. The concept had been adapted for exoplanet hunting, but the engineering challenge was brutal. The mask had to be precise enough to suppress the star's light by many orders of magnitude, without wiping out everything around it. Too large a mask and you block the planet. Too small and the star's light bleeds around the edges. Getting it right required extreme care, and even with a working coronagraph, what came out the other end was not a clean, crisp image. It was faint. It was smeared. It was the kind of data that forced researchers to argue over whether what they were seeing was real. In 2003, a team using the Very Large Telescope in Chile pointed at Beta Pictoris and blocked out the star. What appeared in the data around the masked star was a faint smudge, not a clean disk of light, not a bright point, a smudge. But smudges can tell you things, and this one was in the right place at the right brightness with the right color to be a planet. The team was cautious. They sat on the data. They ran the analysis again. They looked for alternative explanations. Scattered light, instrument artifacts, background objects caught in the field. One by one, the alternatives failed. By 2008, a second set of observations confirmed it. There was something there, and it was orbiting Beta Pictoris. The discovery was published, and exoplanet science had its first direct image. Beta Pictoris b, as it was designated, turned out to be enormous. Current estimates put it at somewhere between 7 and 13 times the mass of Jupiter, which means it sits near the boundary between very large planet and something approaching a failed star. It orbits at roughly 9 astronomical units from Beta Pictoris, comparable to where Saturn sits in our solar system. That distance matters because getting a coronagraph to separate a planet from its star requires physical space. A planet hugging close to its star disappears behind the mask, no matter how precisely you engineer it. Beta Pic b's wider orbit is part of why it was findable at all. The planet is also hot. At roughly 1,700 degrees Celsius, its surface temperature dwarfs anything in our solar system. But this makes sense. The system is only 20 million years old. Beta Pic b has not had time to cool down from the energy released during its formation. It is still radiating that heat outward, which is part of why it glows brightly enough in infrared to be detected against the star's suppressed light. A colder, older planet at the same distance would have been far harder to pull out of the noise. What happened next was something astronomers had never seen before, because the observations kept coming. Teams pointed at Beta Pictoris year after year, and in each new image, Beta Pic b had moved. Not by much, but by enough. A planet taking roughly 20 years to complete a single orbit around its star does not sprint across the field of view. It crawls. But with enough years stacked on top of each other, the motion becomes clear. By the early 2010s, researchers had images separated by enough time to watch the planet visibly arc across the sky relative to the star. You were watching a planet physically orbit another star in real time. Not inferred, not calculated, watched. The sequence of images showing Beta Pic b moving along its orbital path became one of the most reproduced figures in modern astronomy, because it was proof of something humanity had wondered about for centuries and finally had the technology to see. What the discovery did to the field is hard to overstate. Direct imaging had been dismissed as aspirational. Beta Pic b turned it into a research program. Suddenly, there were dedicated coronagraphic instruments being designed for major telescopes worldwide, specifically to chase more of these images. The question shifted from whether direct imaging could work to which systems were most likely to yield results. Young stars became prime targets. Young planets still warm from formation are brighter in infrared, which means they stand out better against the masked star. Nearby stars are better targets because angular separation between a planet and its star grows larger with proximity to Earth. Beta Pictoris hit both criteria. Young system, 63 light-years away, and its success pointed toward other systems with similar profiles. The deeper meaning of Beta Pic b wasn't just what the planet was, it was what the image proved about the universe. For the first time, you had unambiguous visual evidence that other stars had giant planets in wide orbits, sitting at distances comparable to the outer planets of our own solar system. It made the solar system look less special and planetary systems look more common. If Beta Pictoris had a giant planet visible at Saturn-like distances, how many other stars did? And if Beta Pictoris already had this famous disk and now had a confirmed giant planet, what else was hiding in the system that nobody had looked for yet? One planet confirmed, and the system that already had the most famous debris disk in astronomy had now produced the most famous direct image in exoplanet history. But the question of what else might be orbiting out there was very much still open. The second planet wasn't found the way the first one was. Beta Pictoris b had been spotted in a photograph, a faint smudge of light captured after blocking the star itself. That approach worked because the planet was large, warm and sitting at a distance from the star that made it just barely separable from the glare. Beta Pictoris c didn't cooperate with any of that. It sits much closer to the star, in a region where direct imaging at the time was essentially useless. The planet was buried too deep in the stellar light to pull out with a coronagraph, so when the announcement came in 2019, the discovery method was completely different. No photograph, no image at all. What the team used instead is called radial velocity. The basic idea is almost counterintuitive when you first hear it. We tend to think of a planet orbiting a star the way the Earth orbits the Sun. The small thing going around the big thing sitting still. But that's not quite right. A planet's gravity tugs on its star. Every time the planet completes a loop, it pulls the star slightly toward it, then slightly in the other direction. The star doesn't move much. For a planet the size of Jupiter pulling on a star the size of our Sun, the wobble is maybe tens of meters per second. For a star as massive as Beta Pictoris, the numbers are different, but the principle is the same. The star moves, not by a lot, but it moves. Here's why that's measurable from 63 light-years away. When the star moves toward Earth, even slightly, the light it emits gets compressed. Wavelengths shorten. The star's spectrum shifts slightly toward the blue end. When the star moves away, the light stretches. Wavelengths lengthen. The spectrum shifts toward the red end. These shifts are small, tiny fractions of a nanometer, but modern spectrographs are sensitive enough to detect them, and if you watch a star long enough, you can pick out a regular pattern of shifting back and forth that tells you a planet is orbiting and how fast. From that period, and from the strength of the wobble, you can calculate roughly how massive the planet must be and roughly how far out it's sitting. For Beta Pictoris c, the signal was there in years of archival data. The team, led by Anne-Marie Lagrange at the Institute of Planetology and Astrophysics of Grenoble, went back through observations collected over more than a decade and found the wobble, a period of roughly 1,200 days, a mass somewhere in the range of 7 to 10 times Jupiter, an orbital distance of about 9 astronomical units, similar to the region of our solar system between Mars and Saturn, where the asteroid belt sits, well inside the orbit of Beta Pic b, two giant planets in the same system, one found by photograph and one found by watching a star wobble. The obvious next step was to confirm the second one the first way, to actually see it. That confirmation took a few years. Coronagraphic imaging had to be pushed to its limits, and the geometry of the orbit had to be favorable. In late 2020, a team using the Very Large Telescope in Chile managed to directly image Beta Pictoris c, capturing both planets in the same observations, not simultaneously in one exposure. The geometry and brightness differences made that complicated, but close enough that for the first time, astronomers could point at this system and show you two distinct giant worlds, confirmed and photographed, orbiting the same young star. It was the kind of image that makes a scientific case feel settled, except the more you looked at those two planets, the more the questions piled up. Beta Pic C is close to the star. Beta Pic B is farther out, at roughly 9 to 11 times the distance of C. Between them and beyond them sits the debris disk, a sprawling structure that had been studied for decades. With two confirmed planets, theorists went back to their models. They plugged in the masses and the orbits. They ran the simulations. And the disk didn't cooperate. The warp in the inner disk, an angle in the plane of the debris that astronomers had puzzled over since the 1990s, was largely explained by the gravitational influence of Beta Pic B. The general architecture of the outer disk made more sense with a giant planet present, but certain features resisted explanation. The sharply defined inner edge was the most stubborn. There was a boundary, a place where the dense debris disk simply stopped, like a wall. Disk material on one side, relative emptiness on the other. Neither of the two known planets sat in exactly the right position or carried exactly the right mass to account for it cleanly. Their gravity was real, their influence was real, but the math kept coming up slightly off. Astronomers who study disk structure know what a sharp edge like that usually means. Something is clearing it, something with enough mass to gravitationally shepherd debris away, to act as a boundary keeper, sitting right at the transition point between the thick disk and the empty inner region. They ran the numbers. A planet at roughly 30 astronomical units, comparable to where Neptune orbits in our solar system, would produce almost exactly this kind of edge. The problem was that no one could find it. Two confirmed giants, a famous debris disk, and a sharply defined inner edge that neither planet explained, which meant some astronomers had already started looking for something they couldn't yet see. The debris disk around Beta Pictoris was discovered by accident, and it immediately changed how astronomers thought about other star systems. It was 1984. A team of astronomers at the University of Arizona was using a coronagraph, a device that physically blocks a star's central light, to get a cleaner look at Beta Pictoris. They weren't expecting anything unusual. What they found instead was a pale, elongated streak extending outward from the star in both directions. A flat disk of material stretching hundreds of astronomical units into space. At the time, circumstellar disks had been theorized. They had not been seen. This was one of the first times anyone had directly imaged one, and it was orbiting one of the sky's brightest nearby stars. Beta Pictoris went from being an interesting young star to being one of the most important objects in planetary science almost overnight. What the disk actually is took time to understand. It is not a smooth sheet of gas the way early illustrations suggested. Think of it more like a vast, churning construction zone, billions of rocky and icy fragments left over from the early process of planet formation, ranging from dust grains up to objects hundreds of kilometers across. These fragments are not sitting still. They are constantly running into each other, grinding against each other, breaking apart into smaller pieces and replenishing a continuous haze of fine dust that catches starlight and glows faintly across hundreds of astronomical units. The dust itself doesn't last. Radiation pressure from the star pushes fine particles out of the system over thousands of years. What you're seeing when you look at the disk is not a relic, it is an active process. Something is constantly resupplying the dust, and that something is the ongoing collision of countless unseen bodies. When you observe the disk through a large telescope with the star blocked out, it appears as a faint line of scattered light extending from the center outward, roughly edge-on from our vantage point. That edge-on orientation is part of what made it so easy to detect in 1984 and part of what has made it such a useful structure to study ever since. You can measure its brightness profile at different distances from the star. You can look at its color, which tells you something about the size and composition of the particles scattering the light. You can compare the two sides, the northeast extension and the southwest extension, and see whether they match. For decades, astronomers did exactly this, and what they found is that the disk is not what you would call well-behaved. The first oddity is a warp. Near the inner region of the disk, the plane tilts. The outer disk extends along one flat plane, but roughly within 80 astronomical units of the star, the material bends slightly out of alignment, like a vinyl record that has been left in the sun. A warp like this is the signature of a gravitational pull from something that orbits at an angle to the disk's main plane. When Beta Pictoris b was confirmed in the years after its initial imaging, astronomers ran the calculations. The planet's orbit is slightly inclined relative to the disk's outer plane, and that inclination is exactly what would produce the observed warp. Beta Pic b was the gravitational culprit. That piece clicked into place cleanly. The second oddity is an asymmetry. The two sides of the disk don't mirror each other. The southwest extension is slightly brighter and more extended than the northeast side. The distribution of dust isn't symmetric. This kind of asymmetry tends to mean that the density of material is higher in certain regions, which in turn suggests that collisions are happening more frequently in some areas than others. Something is funneling material unevenly. Beta Pic b accounts for part of this. The two confirmed planets together account for more, but partial explanations are not complete ones, and the asymmetry has never been fully described by the planets that were known. The third oddity is the one that matters most to this story, the inner edge. At a certain distance from Beta Pictoris, the disk doesn't gradually thin out the way you might expect. It has a sharply defined inner boundary, a clear cutoff where the disk begins. Inside that boundary, the material thins dramatically. The transition is too clean to be random. In planetary science, a sharp edge in a debris disk is a specific kind of signature. It is what happens when a planet's gravity carves a lane in the material and prevents smaller bodies from maintaining stable orbits in that region. Jupiter does something like this in our solar system. The asteroid belt has structure. The Kirkwood gaps, regions within the belt where asteroids are sparse, exist because Jupiter's gravitational resonances clear those paths. On a larger scale, the same logic applies to Beta Pictoris. Something massive, sitting at the inner boundary of the disk, was acting as a gravitational wall. Astronomers ran the models. They calculated what it would take to produce a boundary that clean, at that distance, in a disk with the density of Beta Pictoris's. The numbers pointed toward a planet sitting at roughly 30 astronomical units from the star. 30 AU is a meaningful number. In our own solar system, 30 AU is right around where Neptune orbits. It is the outer edge of the classical planetary region, the boundary between the domain of giant planets and the more distant scattered disk beyond. Whatever was sitting at that distance in Beta Pictoris was playing the same role Neptune plays in our solar system. Gravitational gatekeeper, the thing that defines where the planetary region ends and the debris begins. But neither Beta Pic b nor Beta Pic c sat at 30 AU. Beta Pic c orbits close in. Beta Pic b sits farther out than c, but still not at 30 AU. The inner edge of the disk had no confirmed owner. Astronomers had a fingerprint and no suspect. They published papers describing what the boundary implied. They wrote the characteristics down. Mass of at least a few Jupiter masses. Orbit near 30 astronomical units. Inclined enough to interact with the disk, but not so dramatically as to reshape the entire structure. The prediction was precise. The search came up empty. Direct imaging couldn't pull it out. Coronagraphic surveys ran into the disk's brightness. Radial velocity measurements couldn't isolate its signal. The prediction was already on paper before anyone found the planet. a world somewhere near 30 AU, massive enough to carve that edge, invisible to every telescope that had looked for it. The James Webb Space Telescope, launched on December 25, 2021, folded up inside a rocket like a piece of origami, and then spent the next month unfolding itself 1,000,000 miles from Earth. That sentence is worth sitting with for a moment. A mirror 6.5 meters across, 18 hexagonal segments coated in gold, each one the size of a coffee table, had to be packed into a rocket fairing roughly 5 meters wide. The only way to make that work was to fold it. Engineers designed a system of hinges and latches that would release in a precise sequence once the telescope was safely in space, unfolding the mirror panel by panel like a flower opening in slow motion. Every single one of those mechanisms had to work. There was no repair mission. There was no crew. If any latch failed, if any hinge stuck, the most expensive scientific instrument humanity had ever built would have drifted off into the dark, permanently useless. The mirror unfolded without a problem. Webb is a joint project of NASA, the European Space Agency, and the Canadian Space Agency. Development began in the mid-1990s. By the time the rocket lifted off on Christmas morning, roughly 25 years and $10 billion had gone into building it. Hundreds of engineers across a dozen countries contributed. The timeline slipped repeatedly. The original launch target was 2007, then 2011, then a series of dates that came and went. Each delay was expensive and embarrassing. When the telescope finally launched, there were engineers who had spent their entire careers working toward that morning and had never seen it fly. The destination was a point in space called L2, Second Lagrange Point. It sits roughly 1,000,000 miles from Earth in the direction directly away from the Sun, a location where the gravitational pull of the Earth and Sun balance in a way that allows an object to orbit stably while keeping pace with Earth as it moves around the Sun. Webb sits there now, always on the night side of Earth, always shielded from the Sun by a 5-layer sun shield the size of a tennis court. That sun shield is not optional. Webb's instruments need to be extraordinarily cold, around negative 233 degrees Celsius for most of them, to detect the faint infrared light they're designed to study. Any heat from the sun would blind them. The sun shield keeps the telescope's instruments in permanent deep cold, while the sun facing side reaches temperatures hot enough to boil water. The reason Webb operates in infrared, rather than the visible light that Hubble primarily used, comes down to what infrared actually is, and what it can do that visible light cannot. Infrared is heat radiation. Everything with a temperature emits it. Dust clouds, which scatter and block visible light, are far more transparent to infrared wavelengths. Infrared passes through them the way radio waves pass through walls. This matters enormously for studying star systems like Beta Pictoris, where any planet you want to observe is buried behind a substantial debris disk. Try to photograph it in visible light, and the disk's scattered glare drowns everything. Look in infrared, and suddenly the disk becomes more transparent, and things hidden behind it start to show up. There's a second reason infrared matters for young planetary systems specifically. Planets don't just reflect light from their star, they emit their own radiation, and young planets emit a lot of it. A planet that formed tens of millions of years ago is still contracting under its own gravity, still releasing the heat of its formation. This makes young planets genuinely luminous in infrared, glowing with internal heat, even if they're too cold to produce any visible light on their own. A planet orbiting Beta Pictoris, a system only 20 million years old, is warm enough that it's essentially a self-illuminated infrared target. Webb is perfectly designed to find exactly this kind of object. What Webb actually does with the light it collects depends on which of its instruments you're using. It carries 4 main instruments, each one designed for different tasks. NICam is the primary camera, capturing images in near-infrared wavelengths. NIRS handles additional imaging and spectroscopy. MIRI, the mid-infrared instrument, extends coverage to longer infrared wavelengths and can observe things that are even cooler and fainter than NICam's range. And then there is NIRSpec, the near-infrared spectrograph, which doesn't make images the way a camera does. It breaks incoming light apart into its component wavelengths, spreading it into a spectrum the way a prism spreads white light into a rainbow. Each instrument has chromograph modes capable of blocking a star's central glare. Together, they give astronomers a toolkit broad enough to approach almost any target in multiple ways simultaneously. The mirror itself is the foundation of all of it. At 6.5 meters across, it collects roughly 6 times more light than Hubble's mirror. More light means fainter things become detectable. It means shorter exposure times for the same depth of data. It means the spectroscopic instruments, which spread the collected light out across many wavelengths and therefore need a lot of it, can still pull faint signals out of the noise. The beryllium used for the mirror segments was chosen because it holds its shape precisely even as temperatures plunge to the extreme cold of deep space. The gold coating was chosen because gold is an excellent reflector of infrared light. Every material decision in this telescope was made with the specific goal of maximizing infrared sensitivity. When the first science images came out in July 2022, the reaction was almost disorienting. Galaxies that had previously appeared as smudges resolved into detailed structures. Objects that had been invisible entirely appeared for the first time. The depth of the images, the sheer number of galaxies visible in a tiny patch of sky, was beyond what previous instruments had produced. Astronomers who had been planning their research programs around Webb's expected capabilities still found themselves surprised by how much it actually delivered. Systems with debris disks and known planets went on the early observation queue because they offered immediate science returns. The instruments were ready, the targets were already identified, the open questions were already written down. Beta Pictoris went on the list early, a famous system with known planets, a famous disk, and open questions that nobody had been able to answer with the instruments available before. To understand what actually happened when Beta Pictoris D was found, you need to understand the instrument that found it. NIRSpec stands for Near Infrared Spectrograph. It is one of 4 main science instruments aboard the James Webb Space Telescope, and in terms of raw scientific versatility, it may be the most powerful of the group. The name tells you most of what you need to know. It works in the near-infrared portion of the electromagnetic spectrum, and it is a spectrograph, not a camera. That distinction matters more than it might first appear. A camera records brightness at each position. You get an image, a map of how much light is arriving from each point in the sky. A spectrograph does something fundamentally different. Instead of simply recording the total light arriving from an object, it spreads that light out by wavelength, the way a prism spreads white light into a rainbow. What you get is not a single brightness value, but a curve, a detailed profile showing exactly how much light is arriving at each individual wavelength across a broad range. Astronomers call this a spectrum, and a spectrum contains an amount of information that a simple image cannot come close to matching. Here is why that matters for planets. Every atom and every molecule in the universe interacts with light at specific wavelengths. When light from a star passes through a planet's atmosphere, certain gases absorb specific wavelengths and leave gaps in the spectrum, dark lines at precise locations that act as a chemical barcode. Carbon monoxide absorbs at wavelengths that water vapor does not. Methane leaves a signature that carbon dioxide does not. These patterns are not subtle. They are sharp, distinctive, and unique. If you have a spectrum of an object and you know what you are looking for, you can read the chemistry of an atmosphere tens of light years away without sending anything near it. This is how astronomers have been characterizing exoplanet atmospheres for years, but almost always for planets that had already been found by other means. The spectrum comes after the discovery, not before. That assumption is exactly what NIRSpec's integral field unit turned upside down. The integral field unit, or IFU, is a specific observing mode of NIRSpec, and it is the component that makes the instrument genuinely unusual. A standard spectrograph gathers light from a single point or a narrow slit, and produces one spectrum. The IFU does not work this way. It captures light from a small patch of sky and simultaneously produces a spectrum for every spatial position within that patch. Not one spectrum, hundreds of them, each from a slightly different location, all collected at the same moment. The way this works involves a component called an image slicer, a set of tiny mirrors that divide the incoming light from the full field of view into thin strips and redirect each strip toward the spectrograph. Each strip gets dispersed into its own spectrum. The result is a three-dimensional block of data that astronomers call a data cube. 2 dimensions of that cube represent position on the sky. The third dimension represents wavelength. Every single pixel in the spatial image carries its own complete spectrum, its own chemical fingerprint, rather than just a brightness value. Think of it this way. A standard camera is like a painting, color and brightness across a surface. A standard spectrograph is like listening to a single instrument in an orchestra. The IFU is like having a microphone at every seat in the concert hall simultaneously and recording every instrument at once, so you can later isolate any sound from any position. The volume of information is almost uncomfortable. For the Beta Pictoris observations, the NIRSpec IFU was covering a region of the sky that included the star, its known planet, and a significant portion of the surrounding system. Every point in that region was generating its own spectrum in real time. This is where the computational challenge comes in. Working with IFU data is not like looking at a photograph. Processing a data cube of this complexity requires sophisticated software specifically designed to disentangle overlapping signals, light from the star leaking across adjacent pixels, the diffuse glow of the debris disk to contributing its own spectrum to every position, instrumental artifacts mimicking faint signals. Pulling a genuine planetary atmosphere signal out of this noise requires knowing what you are looking for and building models precise enough to distinguish a real fingerprint from contamination. The techniques used on this data were not off-the-shelf tools. They were developed specifically for observations like these, built on years of understanding exactly how NIRSpec behaves and exactly what each kind of atmospheric chemistry looks like in the infrared. What makes the IFU approach so different from traditional coronagraphic imaging is precisely this shift in strategy. Coronagraphic imaging blocks the star's light with a physical mask and then tries to detect a planet as a faint point of light against the remaining background. You are looking for brightness. You need the planet to stand out visually, which means the planet has to be brighter than everything around it. In a system cloaked by one of the brightest debris disks known, that condition is nearly impossible to satisfy. The disk scatters light everywhere. The background is not dark. It glows. The IFU bypasses this problem entirely. It is not looking for a bright point. It is looking for a chemical pattern. Dust scatters light, but it does not produce carbon monoxide absorption features. Stellar glare fills the frame with photons, but those photons do not carry methane bands. A planetary atmosphere has a fingerprint that the disk, the star, and every other source in the field simply does not share. If you can measure the spectrum at every position precisely enough, a planet's chemistry will announce itself even in a field that is otherwise blinding. The team that sat down with this data in late 2023 was not looking for a third planet. They were there to study the atmosphere of the planet they already knew about. Aidan Gibbs and his team at UC San Diego were not looking for a new planet when they sat down with an NIRSpec data. They had a specific job. Beta Pictoris b was the target. A giant planet several times the mass of Jupiter, still warm from its formation, glowing in infrared in a way that made it an ideal candidate for detailed atmospheric study. The goal was chemistry. What gases were present? In what ratios? How did the atmosphere of a young giant planet look when you examined it with the most powerful space telescope humanity had ever launched? This was focused, disciplined science with a clear question and a known subject. Beta Pic b had been observed before, of course. Teams had been watching it for years, but NIRSpec's integral field unit offered something previous instruments couldn't. the ability to map the planet's atmosphere across a spatial region and a spectral range simultaneously, pulling out chemical fingerprints with a precision that earlier observations simply could not match. So Gibbs and his collaborator Jean-Baptiste Ruffio set up their observations, pointed Webb at the system, and let the instrument collect its data cube. Every pixel in the field carrying its own spectrum, every position in that patch of sky tagged with its own chemical story. It was, by any measure, a routine observation of a well-understood object. The IFU doesn't look at a single point. That's the thing nobody fully appreciates until they're staring at the data. When the team aimed NIRSpec at Beta Pic-B, they were capturing a region of the system, not just the precise coordinates of the known planet, but everything nearby, all of it simultaneously, all of it tagged with spectral information. The system comes as a package. You cannot isolate one object without the rest of the frame coming along for the ride. In practice, this means the data contains information about regions the team had no particular reason to examine closely. They were there for B. The rest of the frame was, essentially, background. Except it wasn't as the team worked through the data cube, pulling out the spectrum of Beta Pic-B and analysing its chemical content. Something appeared in a different part of the frame. Not where the known planet was, not where the star was, not in a region associated with any recognised source of emission or scattering. Somewhere else. A signal sitting in the data that had no obvious explanation. The shape of it was wrong for dust. Dust-scattered light produces a smooth, featureless continuum, a gradual slope across wavelengths with no sharp features. What the team was seeing had features, peaks and troughs, rising and falling at specific wavelengths, in a pattern that dust cannot produce. This was not background noise. It wasn't an artifact of the instrument. Something in that part of the frame was absorbing infrared light at specific wavelengths and leaving a structured imprint on the spectrum. That pattern is what a planetary atmosphere looks like. The first reaction, in any situation like this, is suspicion. Instruments are complex. Data reduction introduces artifacts. When you run a sophisticated pipeline on a massive spectral cube, ghosts appear sometimes. Reflections of bright sources bleeding into adjacent regions, scattered light mimicking structure, software quirks producing features that don't exist in the sky. The team would have known this immediately. The response to an unexpected signal is not excitement, it's methodical doubt. They checked the position. They examined whether the feature could be a reflection of Beta Pic-B itself, or contamination bleeding in from the star. They looked at whether the pattern was consistent across different exposures, or whether it flickered and shifted in ways that would suggest noise. They tested the signal against known instrument artifacts, looking for any technical explanation that would make it go away. It didn't go away. The pattern held across exposures. It stayed in the same position. Its spectral shape remained consistent with a real astrophysical source, rather than any known instrumental artifact. Whatever was producing those absorption features was genuinely there in that part of the frame, in the Beta Pictoris system, at a location that was not Beta Pic-B, and not the star, and not any other catalogued object in the field. The team checked the known architecture of the system. Beta Pic-B, confirmed, well characterized, accounted for. Beta Pic-C, closer to the star, interior to B's orbit, also accounted for. The star itself, obvious in the data, easily separated. The debris disk, a diffuse smooth background contribution. None of these explained the signal. The signal was something else. At this point, the question becomes stark. If it's not an artifact, and it's not any known source, what is it? In astronomy, when you see a signal with the spectral fingerprint of a planetary atmosphere sitting in a position consistent with an orbit around a young star, there is really only one class of objects that fits. You're not supposed to announce that conclusion to yourself too quickly, but the logic points in one direction. The team dug deeper. They examined the Doppler shift of the spectral features. The fact that the absorption lines were offset slightly from where they would fall for a stationary source. That offset carries information. It tells you whether the object is moving toward you or away from you and how fast. The shift they measured was consistent with an object on an orbital path around Beta Pictoris, moving at the velocity you would expect for something circling the star at a substantial distance. This wasn't stationary contamination. Whatever was producing the signal was moving. It was in orbit. Think about what this means practically. The team had sat down to map the atmosphere of Beta Pic b. They had not submitted an observing proposal looking for additional planets. They had not designed their data reduction pipeline specifically to search for faint companions. They were doing chemistry on a known world, and in the process, the IFU's wider spatial coverage handed them an entirely different discovery, a signal from a different part of the system. A signal that had been sitting in that system for presumably millions of years that nobody had seen despite more than a decade of intensive observation with major telescopes. The Very Large Telescope had looked at this system. Hubble had looked at this system. Ground-based imaging campaigns going back to the early 2000s had examined this system in detail. None of them had found this. Why not? That question would take time to answer fully, but the signal itself was now real. The spectral fingerprint was consistent. The orbital motion was there. The location made sense given what the disk structure had been hinting at for years. A signal pointing toward a giant planet at roughly 30 astronomical units from Beta Pictoris. Precisely the region where theorists had predicted an unseen world might be lurking, based on the disk's sharp inner edge. The prediction was already in the literature. Nobody had found the planet it predicted. Until now, accidentally, while looking at something else entirely. Gibbs and Ruffio had come in to study B. They were leaving with D. The confirmation process still lay ahead. Independent verification, additional instruments, archival data, a second team looking at the same region and arriving at the same conclusion. None of that had happened yet. What the UC San Diego team had in front of them in that moment was a spectral signal they couldn't explain away, sitting in a position consistent with a planetary orbit, produced by an object that had evidently been present in this system throughout every previous observation campaign without anyone noticing it was there. A system that had been studied continuously for over a decade, with some of the best telescopes humanity had ever built, had been hiding a giant world in its data the entire time. The signal that pointed to Beta Pictoris d wasn't faint or ambiguous. It was sitting there in the NIRSpec data, sharp and unmistakable, stamped into the spectrum like a signature someone had forgotten to hide. The team had been pulling apart the light from Beta Pictoris b, studying what its atmosphere was made of, when this second pattern showed up in a completely different part of the frame. Not noise, not an artifact. Something with chemistry. The primary fingerprint was carbon monoxide. This is worth understanding because carbon monoxide is not a subtle molecule. In the infrared, it produces a very specific series of absorption features, a staircase of peaks and troughs at wavelengths that don't match anything a smooth background of dust or scattered starlight would produce. When infrared light from the star passes through a planetary atmosphere carrying carbon monoxide, that gas stamps its pattern onto the light the way a seal stamps wax. The features are distinctive. Astronomers have catalogued them down to precise wavelengths, and when you see them appear in a spectrum, you are not guessing at what you found. You are reading a label. The pattern Gibbs's team pulled from the data matched this signature cleanly. The absorption features were where they should be, with the spacing and relative depths that carbon monoxide produces. It was not one weak line that could be dismissed. It was the full series, the whole staircase appearing in a region of the detector that nobody expected to find a planet. That alone was striking enough. But the signal carried more information than just the chemical identity of whatever was out there. Spectral lines can tell you about temperature and pressure. The strength of an absorption feature depends on how much of a given molecule is present and what physical conditions that molecule is experiencing. A hotter, denser atmosphere produces features of a different shape and depth than a cold, thin one. By fitting models to what the lines actually looked like, the team could start to constrain what kind of object was producing them. The numbers that came back were consistent with a massive gas planet, warm from the heat of its own formation, young enough that it hadn't fully cooled down since the system assembled itself 20 million years ago. None of this pointed toward a background star, a clump of dust, or an instrument glitch. Everything pointed toward a planet. Then there was the Doppler shift. This is where the signal went from interesting to genuinely exciting. If the source of those carbon monoxide lines were stationary relative to Earth, the lines would sit at their rest wavelengths, the exact positions where laboratory measurements say they should appear. They didn't. The lines were slightly shifted, not by much, but by a measurable and consistent amount. That shift is the signature of motion. The object producing those lines was moving along an orbital path, sweeping around Beta Pictoris at a speed that displaced its spectral features by a predictable amount. The Doppler effect is the same reason an ambulance siren sounds higher pitched as it approaches and lower as it moves away. Light does the same thing when its source is in motion. The team worked backward from that shift. The velocity implied by the offset, combined with what was known about the mass of Beta Pictoris, let them estimate where in the system this object had to be orbiting and how fast it was moving. The math pointed toward a distance of roughly 30 astronomical units from the star, 30 times the distance between Earth and our Sun. That placed it considerably farther out than Beta Pictoris b or c, orbiting in a region analogous to where Neptune sits in our own solar system. And 30 AU was not an arbitrary number. That was almost exactly the distance that theoretical models of the debris disk had been suggesting for years. The sharp inner edge of the disk, the feature that the two known planets couldn't cleanly explain, had been pointing towards something sitting right around there. The signal landed in exactly the spot the disk's structure had been quietly marking for decades. This convergence of data points was remarkable. The Doppler measurements, the spectral chemistry, the derived mass from atmospheric modeling, and the orbital architecture all aligned without contradiction. Separate lines of evidence from entirely different physical properties were telling the same story. A substantial planet was orbiting Beta Pictoris at precisely the location where structural analysis of the debris disk had suggested something massive must exist. The detection wasn't achieved through lucky timing or a chance observation window. Rather, it emerged from careful analysis of data that had been specifically designed to study Beta Pic b, only to reveal that an entirely different world had left its fingerprint in the same instrumental frame. What made this so striking was its location in the data. The NIRSpec field of view had captured the known planet B on one side and the star's glare on the other. Beta Picti's fingerprint showed up in the space between, spatially separated from both, in a region that previous surveys had looked through without finding a point source bright enough to flag. It had never appeared as a dot of light against the disk background because the disk's scattered glow swamped it, but the chemical fingerprint of its atmosphere cut through that background in a way that reflected brightness never could. Dust doesn't produce carbon monoxide absorption features. Stellar glare doesn't produce them either. Only a planet's atmosphere does. The team went back through the data multiple times. They checked whether the signal could be explained by contamination from Beta Pic b's spectrum bleeding across the detector. It couldn't. The spatial separation was clear, and the chemistry didn't match B's profile precisely. They checked whether it was a known artifact of NIRSpec's calibration. It wasn't. Every test they ran came back pointing at the same conclusion. There was a third body orbiting Beta Pictoris, and it had been generating this signal all along, hidden not because the signal was weak, but because no one had previously been looking for a planet this way, in this system, at this position. The data existed, the fingerprint was there, it just required the right instrument, asking the right question to become readable. There was something almost unsettling about that. Beta Pictoris has been one of the most intensively observed star systems in modern astronomy. Some of the best telescopes ever built have been pointed at it. Teams from a dozen countries have published hundreds of papers about it. And sitting quietly in the infrared, producing its carbon monoxide signature, a giant planet twice the mass of Jupiter had simply waited. 11 years of continuous scrutiny, and the signal was there in the data any team could have requested. What they needed now was independent confirmation, proof from a second set of eyes using different instruments that what they were seeing was real. Based on what the spectral data can tell us, Beta Pictoris d is a giant, at least twice the mass of Jupiter, possibly more. That number can slip past you without registering what it actually means. Jupiter is not simply the largest planet in our solar system. It is larger than all the other planets combined, by a significant margin. More than 1,300 Earths could fit inside its volume. Every rocky world, every ocean, every mountain range humanity has ever known, all of it could be swallowed by Jupiter 1,100 times over before it ran out of room. Beta Pictoris d is at least twice that. Whatever this planet is, enormous doesn't quite cover it. The mass estimate comes from the spectral signal itself. When a planet moves along its orbital path, the light from its atmosphere shifts slightly in wavelength, depending on whether the planet is moving toward us or away from us. This is the Doppler effect, the same principle that makes a passing siren drop in pitch. By measuring how much the absorption lines in the spectrum shifted, researchers could calculate the planet's orbital velocity, and from that velocity and its position, they could work backward to an estimated mass. The current floor is 2 Jupiter masses. It could be higher. The data will sharpen as observations continue, but the floor is already enough to make Beta Pictoris d one of the more substantial worlds in any nearby system. Its distance from its star is approximately 30 astronomical units. 1 astronomical unit is the distance from Earth to our Sun, roughly 93 million miles. 30 of those puts Beta Pictoris d at about 2.8 billion miles from its star. In our own solar system, 30 AU is Neptune territory. Neptune sits at an average of about 30 astronomical units from the Sun, marking the outer edge of our familiar planetary architecture. Beta Pictoris d occupies an almost identical position in its own system, the outermost known giant, sitting right at the boundary where the planetary region ends and the debris disk begins. That boundary is not a coincidence. The debris disk around Beta Pictoris has a sharply defined inner edge that astronomers have been puzzling over for years. Disk edges like this don't maintain themselves. Left alone, the gravitational interactions between billions of small rocky and icy fragments would cause the disk to gradually spread inward over time. Something has to be clearing that zone, shepherding the material outward and preventing it from drifting closer to the star. Based on the orbital position of Beta Pictoris d, the most straightforward explanation is that this planet is the reason the edge exists. Its gravity sweeps through that region on every orbit, ejecting or redirecting anything that wanders too close. The planet is, in effect, a gravitational gatekeeper, maintaining the boundary the way a dam maintains a water level, continuously and without fanfare. This is something astronomers had actually predicted. Before anyone found Beta Pictoris d, theoretical models of the disk's structure had suggested that a planet at roughly this distance would explain the inner edge. The prediction was on paper. The planet is now confirmed. The match between the two is the kind of result that makes scientists feel like they are reading the system correctly. Now consider what kind of world it actually is. Beta Pictoris is about 20 million years old. In stellar terms, that is very young. In planetary terms, it means Beta Pictoris d formed recently enough that it is still processing the energy of its own creation. When a giant planet forms, it accumulates gas rapidly, and that infalling material releases energy as heat. The planet contracts under its own gravity, and as it contracts, it glows. Young massive gas giants at this stage are not cold, dark worlds like Neptune. They are hot. They radiate. They glow in infrared with the leftover warmth of their formation. Based on its mass and the system's age, Beta Pictoris d is almost certainly warmer than any planet in our current solar system by a significant margin. It hasn't had time to cool. It is still radiating, still contracting slowly, still settling into the configuration it will hold for millions of years to come. This is one of the reasons Webb's infrared instruments can see it at all. A cold planet simply doesn't emit much, but a young massive gas giant still hot from formation glows in exactly the wavelength range where Webb is most sensitive. The planet is in a sense announcing itself, not by reflecting starlight, which gets swamped by everything else in the system, but by emitting its own heat. That heat carries the chemical fingerprints of whatever gases make up its outer atmosphere, and those fingerprints are what the NIRSpec data captured. The spectroscopic analysis revealed crucial details about the planet's atmospheric composition and thermal state. Gas giants at this age contain hydrogen and helium as primary constituents, alongside heavier elements like carbon, oxygen, and trace metals that accumulated during formation. These elements leave distinct spectral signatures in the infrared light the planet emits, allowing astronomers to map the chemical makeup of its outer layers. By carefully passing these signals across different infrared wavelengths, researchers gain direct insight into the conditions that prevailed during the planet's formation and its current state. Such atmospheric analysis would be impossible for a cold, dim world. Only the energetic heat from a young giant makes such detailed investigation feasible from across interstellar distances. The full architecture of the Beta Pictoris system now looks like this. Beta Pictoris sits innermost, orbiting close to the star in the region roughly comparable to our asteroid belt. Beta Pictoris b orbits farther out, at a distance similar to Saturn's position in our solar system. A warm giant that has been photographed directly and tracked moving across multiple years of images. And now Beta Pictoris d sits at the outer edge, at Neptune's equivalent distance, the largest orbit of the three, guarding the inner boundary of the debris disk. Three giant planets, arranged at increasing distances, each one massive, each one young, each one still warm from the process that made it. The system looks almost familiar from a distance. The scale is different, the age is different, and the chaos is still settling. But the basic structure, a sequence of giant worlds stepping outward from a central star, rhymes with what our own solar system looked like billions of years ago. What makes Beta Pictoris particularly striking is not any single property. It is the combination. A planet at least twice Jupiter's mass, sitting at 30 astronomical units, just inside the inner edge of one of the brightest debris disks known, in a system 63 light-years away, young enough to still be glowing with formation heat. The planet that theory said should be there, hidden in plain sight for over a decade, while some of the most powerful telescopes humanity has built stared directly at this system, trying to understand it. For a planet this large, sitting this close to Earth, astronomically speaking, in one of the most watched star systems in modern astronomy, the more interesting question is not what it is, but why it took so long to find. The debris disk is the most obvious answer, and the most important one. Beta Pictoris d orbits just inside the inner edge of the disk, a position that sounds almost convenient until you think about what that actually means for any telescope trying to find it. The debris disk surrounding Beta Pictoris is not a thin, wispy ring of leftover material. It is one of the brightest debris disks ever catalogued. Billions of rocky fragments and icy bodies grinding against each other, constantly replenishing a haze of fine dust that stretches hundreds of astronomical units in both directions from the star. When that dust catches starlight, it scatters it, and scattered light from a structure this luminous creates a bright, diffuse glow across exactly the region of the system where Beta Pic d sits. Any light the planet reflects off its atmosphere has to travel through that haze before it reaches a telescope. By the time it arrives, the signal is buried. Traditional coronagraphic imaging, the technique that found Beta Pic b in the first place, works by physically blocking the star's light to reveal faint objects nearby. It is a brilliant approach for clean systems or for objects bright enough to stand above the scattered background, but pile enough dust-scattered light on top of a planet's reflected signal and the coronagraph stops helping. The background is too bright. The planet's reflected light doesn't rise above it as a clean point source. You end up staring at glare. The disk that made Beta Pictoris famous, the feature that turned it into one of the most important laboratories in planetary science, was also the thing that had been actively concealing one of its own planets. That is the first problem. The second is geometry and brightness. Beta Pic b is a substantial world, several times the mass of Jupiter, still warm from formation, glowing in infrared, and sitting at a closer orbital distance than D. When previous teams aimed their instruments at the system and processed their coronagraphic data, Beta Pic b dominated what they saw. A brighter planet nearby creates its own contamination problem. Some of the light from B bleeds outward in the data. Instrumental artifacts follow bright sources. The region around a known bright planet is exactly the kind of noisy real estate where a second, fainter signal is most likely to go unnoticed. Beta Pic d was sitting in B's shadow, not literally, but in every practical sense that matters for detection. 11 years of observations, and the signal from D was consistently getting washed out by its more conspicuous neighbour. Were there hints in that data? Almost certainly, but hints look like noise when you don't know what you're hunting for. The third reason is the one that cuts deepest, because it isn't about the disk or the geometry, it's about methodology. Coronagraphic direct imaging was the standard approach for this system, and it had earned that status. It found Beta Pic b, it helped confirm Beta Pic c. It produced some of the most iconic images in exoplanet history. The problem is that coronagraphic imaging is optimized for a specific kind of target, something bright enough to show up as a point of light once the star's glare is suppressed. It asks, essentially, can I see this thing? Beta Pic d, sitting inside the disk's edge with its reflected light scrambled by dust, could not answer that question with a yes, not loudly enough to be distinguished from the noise. Spectroscopic analysis asks a completely different question. It doesn't ask whether you can see the planet. It asks whether the planet's atmosphere is leaving a chemical mark on the light passing through the system. Carbon monoxide, water vapor, methane. Each of these molecules absorbs infrared light at specific, characteristic wavelengths. Their fingerprints don't look like dust. They don't look like the star. They don't look like instrumental noise. When the NIRSpec integral field unit mapped the chemistry of the region instead of just its brightness, Beta Pic d had nowhere to hide. The disk couldn't wash out a molecular absorption pattern. Beta Pic b's brightness couldn't contaminate a spectral fingerprint at a different location in the field. The new method wasn't more powerful in the raw sense. It was more specific. It was looking for something the disk could not fake. The planet wasn't invisible. That is the uncomfortable part. It was always there. The signal was always in the data in some form. What was missing wasn't a bigger mirror or a more sensitive detector. What was missing was the right question. Nobody had tried to find a planet in this system, primarily through its atmospheric chemistry, because that approach had never been used as the primary detection tool for a directly imaged planet before. Coronagraphic imaging had the track record. It got the resources, the telescope time, the methodological investment. Spectroscopy was for characterization, for studying planets already found by other means. The assumption was so deeply embedded in how teams designed their observations that even a system as heavily scrutinized as Beta Pictoris could harbor a giant world for a decade without anyone catching it. What this tells you is that the problem wasn't unique to Beta Pictoris. The same blind spot existed for every other system that had been studied using the same standard toolkit. Other disks, other nearby young stars, other cases where a planet sat in exactly the wrong location to be found by the method everyone was using. The debris disk hid Beta Pic d from direct imaging. The brightness of its neighbour buried it in earlier data, and the absence of the right technique meant nobody looked at it with the instrument that could finally read what it was saying. A planet that spends 11 years hiding in one of the most scrutinized systems in astronomy in data that has been sitting in archives available to any team that wanted to look, raises a deeply uncomfortable question. How many others are out there waiting for the same thing? When a discovery is real, other teams find the same thing. The Gibbs team at UC San Diego had their signal. They had gone through the data carefully, ruled out instrument artifacts, ruled out contamination from known sources, and convinced themselves that what they were seeing was a genuine planetary atmosphere. But a single team finding a single signal in a complex dataset is not by itself a discovery. Science doesn't work that way. Before Beta Pictoris D could be called real, someone else had to find it independently, using different tools, asking different questions, arriving at the same answer through a completely separate path. And that is exactly what happened. Ben Sutcliffe and Marcus Bonce, leading a Scottish and German research team, were working on Beta Pictoris from an entirely different direction. They weren't using Webb. Their instrument of choice was the European Southern Observatory's Very Large Telescope, which sits on Cerro Paranal, a mountain in Chile's Atacama Desert at an elevation of about 2,600 meters. The Atacama is one of the driest places on Earth, which matters enormously for astronomy. Water vapor in the atmosphere absorbs infrared light before it ever reaches a telescope's mirror, and up on Paranal there is almost none of it. The VLT is actually 4 separate telescopes, each with an 8.2 meter primary mirror, capable of operating individually or in combination. It is one of the most powerful ground-based observatories on the planet, and it had been pointed at Beta Pictoris many times over the years. The European team pulled together VLT observations and combined them with data from Webb's NIRcam, the near-infrared camera, a different instrument entirely from the NIRspec IFU that Gibbs had used. NIRcam takes images rather than spectra. It is looking for point sources of light rather than chemical fingerprints. The fact that 2 fundamentally different instruments, capturing different kinds of information, both pointed toward the same object in the same place, was the first serious sign that this was not a fluke. The orbital parameters matched, the mass estimates matched, the location matched. 2 teams, 2 continents, 2 approaches, same planet. One of the European researchers described the experience of finding it as the planet having played hide-and-seek for 11 years. That phrase is almost too casual for what it actually means. 11 years is a long time in astronomy. In that window, dozens of teams had looked at Beta Pictoris with serious instruments and serious intentions. The system had been one of the most scrutinized in the field. Papers had been written, conferences had featured it, careers had been partly built on studying it, and the whole time a giant world at least twice the mass of Jupiter was sitting there in the data, unrecognized. When Sutcliffe and Bonce's team went back through the VLT archive, years of observations collected without any knowledge of what they might contain, they found traces of it. Not obvious, not screaming for attention, but there. The signal existed in data that had already been collected, processed, and set aside. Nobody had identified it because nobody had been looking for it in the right way. The techniques being used on those older datasets weren't tuned to pull out an atmospheric fingerprint buried inside a bright disk environment. The planet wasn't absent from the record. It was present and invisible at the same time, the way something can be clearly written in a language you haven't yet learned to read. This is what made the archival finding particularly striking. It wasn't that previous instruments had been too weak. The VLT is not a primitive telescope. It wasn't that previous researchers had been careless or incurious. The teams who had worked on this system were meticulous. The issue was purely methodological. A specific analytical approach had not been applied, and without it, the signal stayed buried under everything else the system was producing. The confirmation didn't stop with the VLT and NIRcam. A second round of Webb observations using both the NIRSpec instrument and the mid-infrared instrument known as MIRI added another layer of validation. MIRI operates at longer infrared wavelengths than NIRSpec, which means it's sensitive to different temperature regimes and different molecular features. Having a consistent signal across NIRSpec's wavelengths and Meyer's wavelengths together is considerably harder to explain as noise or artifact than a signal appearing in just one instrument. The planet had to be producing real emission across a broad range of the infrared spectrum for both instruments to pick it up. It was. What you end up with, after all of this, is a finding that had been verified by NIRSpec spectroscopy, by NIRCam direct imaging, by MIRI mid-infrared observations, by VLT ground-based data, and by independent archival analysis. Each of those is a separate check. Each one could have failed to show the same thing. None of them did. In astronomy, when a major discovery gets published, it is possible for a single study to announce a finding and have the field accept it, particularly if the team is credible and the data is clean. But the Beta Pictoris denouncement arrived differently. Multiple independent papers were published simultaneously, each one covering a different facet of the same discovery, each one with a separate set of researchers who had arrived at the same conclusion without coordinating their findings. That kind of simultaneous convergence is one of the strongest validations a discovery can receive. It means the result is not leaning on one team's judgment, one instrument's quirks, or one analytical choice. Multiple instruments, multiple teams, multiple methods, one answer, and somewhere in the VLT archives, traces of Beta Pictoris d had apparently been sitting unread for years, waiting for someone to know what to look for. The most important thing about the discovery of Beta Pictoris d is not the planet itself. The planet is remarkable, certainly, but planets get discovered. What doesn't happen often, what has arguably never happened quite this way before, is a planet being found primarily through the chemical signature of its atmosphere before anyone confirmed it as a visible point of light. That is a different kind of discovery entirely, and it changes things in ways that reach far beyond a single star system 63 light-years away. To understand why, you need a quick map of how astronomers have been finding planets for the past 3 decades. There are essentially 2 roads. The first is indirect detection, methods that don't see the planet at all but measure its gravitational or optical effect on the star it orbits. Radial velocity tracks the tiny wobble a planet induces in its star's motion. The transit method watches for the slight dimming when a planet crosses in front of the star. Both of these have found thousands of worlds. Neither of them actually sees the planet. The second road is direct detection, physically capturing light from the planet itself. Coronagraphic imaging is the main tool here. A coronagraph blocks the star's blinding light and lets astronomers search the surrounding area for faint companions. This is how Beta Pictoris b was found. It is extraordinarily difficult, and it requires the planet to be bright enough to stand out against whatever background remains after the star is masked out. That second requirement turns out to be a serious problem. Spectroscopy has always lived on the characterization side of this equation. Once you find a planet by some other method, you point a spectrograph at it and start reading its atmosphere. You measure its temperature. You identify its chemistry. You figure out what it's made of. Spectroscopy was the tool you reached for after the discovery, not the tool that made it. What Aidan Gibbs and his team demonstrated with Beta Pictoris d is that this assumption was wrong. Spectroscopy can find the planet first. It can detect the atmospheric fingerprint of a world that nobody has confirmed as a point source object. That particular sentence has never been written about a directly imaged planet before, and the implications are substantial. Here is why dusty systems have been such a persistent problem. A debris disk is not empty space. It is billions of fragments and particles constantly colliding, grinding down into finer and finer dust, scattering starlight in every direction. When you point a coronagraph at a system like Beta Pictoris and block out the star, what you're left with isn't dark sky. You're left with a bright, complex, structured glow coming from all that scattered light. A planet somewhere in that disk has to be bright enough to stand out above the disk's own luminosity. If it isn't, if its reflected light blends into the background, it disappears. The disk defeats the method. This is not a marginal effect in systems like Beta Pictoris. The disk is one of the brightest debris structures known. Traditional imaging was fighting an opponent it couldn't outrun. Spectroscopy doesn't play that game. It isn't looking for a bright point of light. It's looking for specific patterns in wavelength, absorption features stamped onto the spectrum by particular molecules in a planet's atmosphere. Carbon monoxide absorbs infrared light at a very precise series of wavelengths. Water vapor has its own fingerprint. Methane has its own. Each molecule writes its signature onto the spectrum in a way that is chemically distinct and not reproducible by dust scattering or stellar glare. Dust scatters light, but it doesn't create carbon monoxide absorption bands. A star's halo glows, but it doesn't produce methane features. The chemical fingerprint of a planet's atmosphere is, in a meaningful sense, immune to the background noise that defeats direct imaging. Think of it this way. Imagine you are trying to find one specific person in a stadium packed with thousands of people, with bright floodlights washing everything out. Looking for their face is nearly impossible. The glare blends everything together, and individual features disappear into the crowd. But if that person has a voice that is genuinely unlike any other, a particular accent, a specific pitch that no one else in the stadium produces, you can isolate them through the din. You are not looking for their appearance anymore. You are listening for something that only they can produce. That is what moderate resolution spectroscopy does in a system full of scattered light. It listens for voices that dust cannot fake. The word moderate resolution matters here. High-resolution spectroscopy exists and can distinguish molecular features with extraordinary precision, but it requires very bright targets and long observation times. Low-resolution spectroscopy spreads the light less finely and can miss subtle features or confuse overlapping signals. Moderate resolution hits a practical balance, fine enough to identify specific molecular fingerprints clearly, efficient enough to work on targets that are not overwhelmingly bright. This is the mode NIRSpec was operating in when the team pulled Beta Pictoris out of their data. It's a regime that turns out to be well matched to exactly the class of planets that coronagraphic imaging struggles with. What this means going forward is not subtle. Every major young star with a prominent debris disk has, until now, been resistant to complete planetary census. Bright disks obscure planets, the imaging tools that work beautifully on clean, low-dust systems fail in complex, dusty environments. So astronomers have been stuck. The youngest systems, the ones most valuable for understanding how planets form, are also the messiest, and the mess defeats the primary tool. Spectroscopy inverts this problem. The very environments that choke coronagraphic imaging, rich with molecules full of chemical complexity, are exactly the environments where atmospheric fingerprints are most distinct. The chaos becomes signal rather than noise. There is also a practical dimension here that goes beyond future observations. The NIRSpec integral field unit captures spectral information from an entire spatial patch simultaneously. It doesn't look at one point and then move to the next. It gets everything at once. This means that archival data from IFU observations, data already collected, already sitting on servers, might already contain the atmospheric fingerprints of planets nobody has identified yet. Researchers don't necessarily need new telescope time to apply this method. They need new analysis. They need someone to look at existing data cubes and ask whether there are chemical signatures in unexpected positions. The discovery pipeline for this technique doesn't start with an observation request. It can start with a hard drive. That changes the economics of exoplanet discovery in a way that is genuinely unusual. Most new detection capabilities require new instruments, new missions, new funding cycles. This one can run backward through years of archived observations with the right software and the right questions. How many systems have already been observed with IFU spectrographs? How many of those observations contain planets that nobody recognized because nobody was looking for an atmospheric fingerprint rather than a point of light? The honest answer is that nobody knows, and the not knowing is the interesting part. Every young star with a debris disk, every system that has resisted traditional imaging, just became a candidate for a new search using atmospheric fingerprints instead of point source brightness. Beta Pictoris is not an obscure star. It has been in serious scientific literature since the 1980s. It produced the first directly imaged debris disk. It gave astronomers the first widely confirmed direct photograph of an exoplanet. Generations of researchers built careers studying it, and yet sitting inside all of that data, orbiting inside one of the most watched systems in the sky, was a giant planet that nobody found for 11 years. That is not a small thing. That is a signal. The question it forces is straightforward. If Beta Pictoris hid a world this size for this long, how many other star systems are doing the same thing right now? The honest answer is that there is no clean way to know, but the evidence suggests the number is not small. Across the galaxy, young stars with debris disks are common. Astronomers have catalogued hundreds of them within a few hundred light-years of Earth alone. A significant portion of those disks show structural features that don't fully make sense without invoking unseen planets. Gaps where material has been cleared, warps that suggest a gravitational pull from something off the disk's plane, asymmetries where one side of the disk is brighter or more extended than the other, sharp edges where the density of material drops suddenly, as if something is sweeping the region clean. Each of those features is a gravitational fingerprint, and for years the working assumption was that the planet responsible would eventually show up in a direct image. Beta Pictoris d suggests that assumption was optimistic. Take AU microscopii. It sits just under 32 light-years from Earth, which makes it one of the closest young stars we can study in detail. AUMIC is only around 22 million years old, roughly similar in age to Beta Pictoris, and it hosts a debris disk that has been extensively mapped. The disk has ripple-like structures in it, fast-moving features that appear to propagate outward through the material. Astronomers confirmed 2 planets around AOMIC, AOMIC B and AOMIC C, both close in, both in orbits well inside the debris disk's main structure. But the inner disk is disturbed in ways those 2 planets don't fully explain. There are brightness asymmetries. There are clumps. The 2 known worlds account for some of the dynamics, but not all of them. The same spectroscopic approach that found Beta Pic d, analyzing the atmospheric fingerprint of a planet hidden against a complex background, has never been systematically applied to AUMIC's outer regions. Whether something is waiting there in existing data is genuinely unknown, but the structure of the disk argues that the system may not have finished giving up its secrets. Fomalhaut is further away, about 25 light-years, and older, somewhere around 440 million years old, which puts it past the chaotic early phase and into a more settled configuration. Its debris disk is striking, a bright, narrow ring offset slightly from the star, with a sharper inner edge than you would expect from a symmetric structure. Astronomers used that asymmetry and edge sharpness for years to argue that an unseen planet must be sculpting the ring. In 2008, a direct imaging team announced they had found it, a point of light designated Fomalhaut b, and it made headlines worldwide. Then things got complicated. Follow-up observations showed Fomalhaut b fading over time in visible wavelengths, and it wasn't detectable in infrared the way a planet of its proposed mass should have been. The current consensus is that what was detected was likely a cloud of debris from a recent collision, not a planet at all, which leaves the ring structure still unexplained by any confirmed planetary body. The sharp inner edge of the Fomalhaut ring, offset and narrow, is exactly the kind of feature that a planet orbiting near that boundary would produce. Whether that planet exists and whether its atmospheric fingerprint is already buried somewhere in archival data from Herschel, Spitzer or Webb Zone instruments, nobody has fully checked using methods like the ones that found Beta Pic d. HR 8799 presents a different kind of problem. This system sits about 130 light-years out and contains 4 directly imaged giant planets. The largest confirmed directly imaged multi-planet system found before Beta Pictoris became a 3-planet system. HR 8799's 4 worlds, designated B through E, are massive warm and spectacular. The system has been studied intensively, and the 4 planets' atmospheres have been characterized using spectroscopy in some detail. But HR 8799 also has a debris disk, and that disk has structure in its inner region that the 4 known planets don't entirely account for. The inner disk appears more extended and disturbed than the 4 outer giants would produce through their gravitational influence alone. Models have suggested that a 5th planet, potentially sitting closer in, might explain the inner disk's structure. It would be smaller, cooler, and harder to detect through conventional coronagraphic imaging. HR 8799 gets a lot of telescope time. Researchers have been trying to image a 5th planet there for years without success. The spectroscopic approach now looks like a plausible avenue for finding it, specifically because the difficulty isn't the disk glare, it's the proximity to the star. Chemical fingerprinting at close separations is exactly what NIRSpec's integral field unit handles without relying on perfect starlight suppression. The common thread through all of these systems is that their known planets don't fully explain their disk structures. This is not a coincidence or a flaw in the modelling. It is a pattern. Disk structure has been pointing astronomers toward unseen planets for decades, and for decades the response has been to look harder using the same direct imaging approach that the debris disk itself defeats. The spectroscopic method inverts the problem. Instead of trying to see the planet through the glare, you look for what the planet's atmosphere is saying. The chemical signal cuts through the disk background in a way that reflected light can't. The disk doesn't produce carbon monoxide absorption lines. The star doesn't produce them in the same pattern. A planet's atmosphere does, and that fingerprint is readable even when the planet itself is invisible as a point source. What makes this genuinely pressing is not just the future observations it enables, but the past observations it puts in a new light. Webb has been operating since 2022. Before Webb, Hubble and Spitzer spent years observing young systems. The VLT and its instruments have collected thousands of hours of data on nearby debris disk systems. Some of that data was gathered in modes that could, in principle, contain the spectral fingerprints of undiscovered planets, signals that were processed for their primary scientific purpose and then archived. Nobody was looking for atmospheric fingerprints from unseen planets in that data because the technique wasn't proven. It is proven now. The implication is that a significant fraction of the planets that will be found in the next decade are already sitting in data that has been collected, archived, and never properly interrogated with this technique. The discovery of Beta Pictoris d is not a conclusion. It's the opening of a research program that could run for the next 20 years. The immediate next step is straightforward. Point Webb at the system again, longer, with more precision. Extract everything the signal still hasn't told us. The team plans to do exactly that. More observations, more NIRSpec time, more data to stack against what they already have. What they're chasing now are 3 things: temperature, composition, a better orbit, and each one unlocks a different piece of the story. Temperature comes first, because temperature is the most direct window into what the planet is doing internally. Beta Pictoris d is 20 million years old. At that age, a giant planet with at least twice Jupiter's mass hasn't finished contracting. It's still slowly shrinking under its own gravity, and that process releases heat. The planet should be glowing, not in visible light, but in infrared, radiating warmth left over from its formation, the way a fire still puts out heat hours after the flames die down. The question is, how much? A precise temperature measurement tells you the rate at which the planet is cooling. That constrains how far along it is in its formation. That in turn pins down the timeline of the whole system's development. If Beta Pic d is hotter than models predict, the planet may have formed later than the others or through a different process. If it's cooler, it may have formed earlier and is further along its evolutionary path. This is not a small question. It connects directly to how and when giant planets form in young debris disk systems, which is one of the central unsolved problems in planetary science. Atmospheric composition is the harder measurement and the more interesting one. The NIRSpec data already showed carbon monoxide. That was the fingerprint that gave the planet away. But carbon monoxide is only one line in a much longer paragraph. Continued observations will look for water vapor, methane, carbon dioxide, other molecules that leave their own distinct marks in the infrared spectrum. The ratio of these compounds, carbon to oxygen ratios, the relative abundance of different gases, carries information about where in the disk the planet formed. Planets that assembled far from their star, in the cold outer regions where ices are stable, end up with different chemical inventories than planets that formed close in, where only the most heat-resistant materials survive. Reading Beta Pictoris' atmospheric chemistry is like reading a shipping label that tells you where the package was built. Even if it's been moved since, orbit refinement matters because the three-planet system is not a static object. Beta Pictoris B, C, and D are all massive, all in relatively close gravitational proximity on astronomical scales, all young enough that their orbital relationships may not yet have settled into long-term stability. A precisely measured orbit for D tells you how its gravitational pull interacts with the other two planets, whether the three are locked in orbital resonances that stabilize them, or whether the system is still shuffling and will eventually eject one of them into a wider trajectory or deeper toward the star. 30 astronomical units is an interesting place to sit. It puts Beta Pictoris right at the inner edge of the debris disk. That itself implies that the planet's gravity is maintaining that sharp boundary. A better orbit pins down that mechanism more rigorously. It also gives researchers a long baseline to compare against future observations and watch the planet physically move, the same way Beta Pic B's orbit was tracked over years of direct imaging. Beyond Webb, larger instruments are coming. The extremely large telescope, currently under construction in the Atacama Desert in Chile, will have a primary mirror roughly 39 meters across, more than 6 times the diameter of Webb's 6.5 meter primary. It will combine that enormous light-gathering area with adaptive optics, technology that corrects in real time for the blurring effects of Earth's atmosphere, producing images sharper than anything currently achievable from the ground. When the ELT comes online later this decade, Beta Pictoris will almost certainly be near the top of its target list. The combination of spatial resolution and spectroscopic capability will push planetary characterization into detail that makes current measurements look approximate. Future space missions are being designed with exoplanet atmospheres as a primary science goal, not a secondary one. What was a specialized capability in Webb's instrument suite may become the central purpose of whatever comes next. The NIRSpec IFU approach itself is already being prepared for broader application. A deliberate survey of young stars with debris disks, the same class of systems as Beta Pictoris, the same age range, the same disk-dominated environments where traditional imaging has struggled, is now conceivable in a way it wasn't 2 years ago. The method works. It found something in one of the most challenging environments you can choose. Every other system in that category now deserves a second look. Not with coronagraphs hunting point sources of light, but with spectrographs hunting chemical fingerprints. The survey is going to find things, and running through all of it is Beta Pictoris, the planet that made the system famous in the first place. The planet Gibbs's team was actually studying when they stumbled onto its hidden neighbor. Beta Pic B and Beta Pic D are now both targets for the same kind of atmospheric analysis. Same star, same age, same formation environment. But B is several times more massive, sits on a tighter orbit, has been accumulating its observational records since 2003. Comparing the two atmospheres, what gases each one holds, what temperatures each one runs, how their chemistry diverges despite starting from the same raw material in the same system, is a natural experiment that no mission had to design from scratch. The data is already partly there. The questions are coming into focus. The planet that started everything, the first directly imaged exoplanet, the reason teams were pointing Webb at Beta Pictor is in the first place, is now sharing the spotlight with a neighbor it apparently had all along. Step back from the details, and what this discovery really represents is simple. a team pointed the most powerful space telescope ever built at a system they already knew well to study a planet they had already confirmed, and found something that had been there the entire time, not at the edge of the observable universe, not buried in the light of some distant galaxy, 63 light-years away, in a system with a famous disk and 2 famous planets and decades of careful attention from some of the best observatories on Earth. And it was hiding anyway. The lesson people want to take from Beta Pictoris d is that we need better telescopes. That isn't quite right. The lesson is that we need better questions. Webb's mirror isn't dramatically larger than what came before it. What changed was the instrument, the mode, and the method. NIRSpec's integral field unit wasn't asking whether there was a bright point of light in this patch of sky. It was asking what chemicals were present and where and how fast they were moving. That is a different question. It got a different answer. Young planetary systems are exactly the hardest places to use the old approach. They're full of dust. Their disks scatter light in every direction. Their known planets are bright and dominant and tend to swamp everything around them. Coronagraphic imaging, which depends on blocking the star's glare to reveal faint reflected light, was never well suited to environments this messy. Spectroscopy doesn't care about scattered light. Dust doesn't produce carbon monoxide absorption bands. Stellar glare doesn't mimic the infrared fingerprint of a warm planetary atmosphere. The chemistry speaks for itself, even through the noise. So the question that actually matters now is a quiet one. How many systems have already been observed, carefully and repeatedly, with instruments that were asking the wrong question? How many archives contain years of data with planetary fingerprints buried inside them, waiting for someone to run a different analysis? Beta Pictoris d had been sitting in detectable form for at least 11 years. Researchers went back through VLT data and found traces of it that nobody had recognized. The signal was there, the planet was there, the tools to find it were almost there, almost. Look up on a clear night. The stars you can see are not empty points. Most of them almost certainly have something orbiting them. Some of those systems have been watched for years. Some have disks. Some have structural features pointing toward planets that haven't been confirmed. The Beta Pictoris story didn't end with Beta Pictoris d. It ended with a method that works, pointed at a sky full of systems that haven't been searched with it yet. Whatever is orbiting out there in the data we have already collected, we just learned how to read a language we did not know we had been hearing.